All right, let's take a look at the chapter 11.1 notes on chi-square goodness of fit tests. So this brings us to a new type of distribution called chi-squared, and we'll talk a little bit about it here in the bottom. But basically chi-squareds type problems, what we'll take a look at least this first one, which is called the goodness of fit test, we'll take a look at situations where we're going to compare the proportions of multiple, or let me rephrase, we're going to compare multiple proportions of successes within a population. So as it talked about, or it says here, what if we want to examine the distribution of a single categorical variable in a population? So we have one population, so I like to think about this as one population with many proportions. Okay? When that occurs, we're talking about a goodness of fit test. So the example here says, are birth weights evenly distributed across the days of the week? The one thing I don't like about this example is weights is actually dealing with a mean. Instead of saying birth weights, maybe the number of births would be more appropriate. Because if it was evenly distributed across the days of the week, then we would expect 1/7, and that would be the proportion for each and every day. So then we could go out and collect a sample and see, does that sample, okay, is that basically the same as what we would expect? So that's what the goodness of fit test looks like. Now what happens is, our distribution is not a normal distribution when we deal with it. It's this distribution that's called a chi-square distribution. So some of the characteristics of a chi-square distribution. As they say here, it's a family distribution that only takes on positive values, and this is kind of the key. They're skewed to the right. Okay? So all chi-square distributions, well I really shouldn't say all, but the vast majority of them are skewed right distributions. Okay? What happens is your chi-square distribution are going to give you that same concept of degrees of freedom. It will fluctuate from problem to problem, and we'll talk about what our degrees of freedom here will be in a goodness of fit test in just a little bit. So, a chi-squared graph will always begin at 0 on the x-axis except for the degrees of freedom of 1. So when that happens, you have this almost like this inverse variation model, so that's your chi-squared curve. But if you look here for like degrees of freedom here of 4, degrees of freedom of 8, you get a skewed to the right distribution. But one of the things that I want you to know, as n, or I shouldn't really say n, your degrees of freedom increases, okay, your chi-squared distribution starts to become more normal. Now, we'll never use the normal distribution for a chi-squared, but you can already start to see skewed right, a little less skewed right here from degrees of freedom of 4 to degrees of freedom of 8. Okay? So how do we approach a goodness of fit test? So if we turn to the next page, you have again, we go to our favorite 4-step process, which you love to do, but it's really helpful because it gives you a process step by step. So when you do the state part, you can decide whether to state it in words or symbols. I prefer to do words. I think it's a little bit easier to do it, but you can do symbols. So what I do is I'll just simply state the specified distribution that was given for the categorical variable is correct. Question is, do we collect a sample that is so different than what we expect that it causes us to suspect or show statistical evidence that it's not correct? So if you're using the symbols, you would define each of the proportions within the population here. So it all depends on how many of you there are, and you got to define them all, and then you got to say that at least one of them is off kilter. And we'll talk about how you can look and see which one is causing the greatest change within the sets of proportions. So we call it a chi-squared goodness of fit test. So we want to make sure that we're using that, because in 11.2 we're going to talk about two other types. When we talk about the conditions, very similar to all the other ones, since it's not normal, we don't talk about it being normally distributed, but we talk about having a large sample size. So random and independent basically stay the same, but what we talk about instead of being normal is we need to make sure our sample size is relatively big. We want to make sure all the expected counts are at least 5. So there's a difference between the observed counts and expected counts, and we'll have to show you how to calculate out the expected counts. It's not actually a hard thing to do, but you just basically take the proportion of what you would expect and times it by the sample size to get your expected amounts. So now we calculate out the chi-squared statistic. The chi-squared statistic very much in a similar formation as when you're doing like a one sample t or one sample mean, but your chi-squared statistic, here we're actually doing the sum. So you take each observed minus the expected, so you're looking at the actual difference between the observed minus the expected. So you kind of think about it like your residual being squared, divided by the expected value. So it weights each and every actual value within each set of the proportions. So now what you do is you take that chi-squared statistic, and on your calculator you can do this function called chi-squared CDF. What you'll do is you'll actually do your chi-squared statistic to positive infinity, and then you'll do your degrees of freedom. So you can kind of see here on your graph, here's your shaded region with your chi-squared statistic to get your p-value. So you can use this function on your calculator. Now your degrees of freedom, we like to define it as k minus 1, where k is the number of proportions in the population. Basically what we're saying is how many different groupings are there within that population that you're taking a look at. So like in that birth number of births within the days of the week, there was actually 7 different days you could be born on. So your degrees of freedom would have been 7 minus 1 or 6. Okay. Conclusion is basically the same thing as we've done before. So you look at p-value, reject if it's less than 5%, fail to reject if it's 5% or more, and we're good to go. So let's go ahead and jump into, I believe, a couple examples here so that you kind of get an idea of how the problem works. So as I go to the next page, I do have it all written out, but I'll do like I normally do, and I'll actually do it this way. I'm going to pull down the black screen here, so it's a little bit different here, so that you can see it as we go. So we'll see if this works out just fine. So here's how the problem basically for this first example. So it says, according to the 2000 census of U.S. residents aged 20 years and older, and this first one should have said in this little typo, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, and 22.8% are 60 years and older. So you can think of all of these that they just gave you as the population proportions. Okay? These are our expected proportions. This is what we would expect from the U.S. population. Table below shows the age distribution for a sample U.S. residents aged 20 years and older. Members of the sample were chosen by randomly dialing landline telephone numbers. So the question becomes, do the data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents? So basically we're kind of looking at landline usage, comparing it to the age. And is the age distribution the same in the United States as it is for those who would actually answer landline surveys, at home? So like in our household, we don't even have a landline anymore, and many more people are going that direction. So it'd be interesting to see if it's actually different. So the null hypothesis would say the distribution of people who answered landline telephone surveys is exactly the same as the age distribution of all U.S. residents. They are equal to each other. That is what we would expect. Or their differences is so small between what we expect and what we observe that we would consider them the same. The alternative then would say they are not the same. Okay? So the question will be, is the variability between age groups so great that it makes us wonder or suspect that something out of the ordinary is happening? So there's our state. Okay? So you may have to pause occasionally in this video to get it because I'm going to kind of rifle through these quickly so the video is not 2.5 hours long. So now, the do part, or I'm sorry, I'm skipping there. We got to state the plan. So we got to state the test. So this will be a chi-squared goodness of fit test. So chi-squared goodness of fit. Chi-squared, I apologize, the symbol is kind of like a squiggly X squared goodness of fit test at our significance level 5%. That's our alpha. So we go through our conditions. Well, if we look up here, we had a simple random sample of 1,048 U.S. adults or U.S. residents, so that's good to go. Then we have to calculate out our expected counts. So what I have to do to get my expected counts is I have to go up here and go 19.1% and 21.5 and 21.1 and 15.5 and 22.8, and I have to multiply all of those proportions by 1,048 and get the actual expected counts. Okay? So if you take a look here, that's basically what I have done. So if it helps you, this 19.1 times 1,048, we expected to get 200.2 adults. We expected to get 225.3 adults in their 30s. In their 40s, we expected 221.1. We expected to get 162.4. And then on the last one, we expected to get 238.9. So we do want to keep the decimals. I know we can't have tenths of a person, but again, we're looking at the theoretical probability of getting this. So we want to try to be as accurate as possible. So as you start to look at this, again, these are the expected based on the US population based by age groups. So you can start to see, wow, we expected a lot more than what we got in the 20s and 30s. 40s was pretty almost dead on, but 50s and 60s we got a lot less. The question is this statistically significant? What's the probability of getting a distribution like this that we have up here, or expected accounts? I apologize. What's the probability of getting a sample like this that we have here in the table, or one that has even more farther away, more diverse distribution from what we would expect? And that's what you do in the chi-squared statistic. So next part here is we're going to, calculate out the chi-squared statistic. But guess what Mr. Bartz forgot to do? You're probably already going, hey, Mr. Bartz, you're forgetting the independent piece. Yep. So let's get that down. So we are sampling without replacement because once a person is selected, they won't be a part of the survey again. So we check if the population is greater than 10 times the sample. And yes, there's at least 10,480 U.S. residents. Okay. So now, going to the do part, this is again where we are calculating out the chi-squared statistic. All right, so calculating out chi-squared. Observed minus expected squared divided by expected. So to get the chi-squared, what I do is I go up top. I observed 141 people in their 20s. I expected 200.2. I squared, divide by 200.2. I do the same thing again, okay, for the second one, and the third one, and the fourth one, and the fifth distribution. So I have to calculate all these out and add them up. So when I do, okay, if you trust my math, it becomes 48.2. So then what I can do to get my p-value is chi-squared CDF. I'm going from 48.2 standard deviations to 999 with a degrees of freedom of 4. this is basically 0. Just to show you on the calculator, I can probably pull it up here. So to do chi-squared on your calculator, second bars, okay, and it's number 8, chi-squared CDF, 48.2, comma 999, comma my degrees of freedom, in this case was 4 because I had 5 groups, 5 different age groups, minus 1 gives me my degrees of freedom of 4. So you can see here it's 8.57 times, e to the negative 10. So I'm going to just kind of write that down here. It was 8.57 times 10 to the negative 10th power. So you can see why I'm saying that this is basically 0. So you can see here I drew a little sketch of my chi-square distribution, 48.2. It would be technically way off the charts, way over here. Degrees of freedom, 5 minus 1 equals 4. I get my value. Okay? So, just like we've done before, our conclusions, interpret P in the context, say we reject or fail to reject, and what does that mean in the context of the problem. So again, interpreting our p-value, we're going to say our sampling distribution result, basically our sample result from 1,048 U.S. residents, or one more extreme, that are farther away from our expected values, would almost never occur if the null hypothesis was true. Since our p-value is less than 5%, we're going to reject the null hypothesis, meaning we do have statistical evidence that the distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents. Kind of something we probably suspected, considering the way communications, especially with landline telephones, has been changing over time, considering how many more and more people are just working with their cell phones and only using cell phones as their form of communication. I know we do that at home now. In our house, we do not have a landline. No, we feel like there's no reason to have it. All right, so that is the first example. All right, on the second example, I would suggest that you pause the video, try it yourself, or at least do each step, and then see how yours matches with mine. But I do love this problem because, I just kind of like the whole context of it because it talks about gambling. So, all right, I'm going to flip over to the last example here. Hopefully it'll let me do it. So let's take a look here. All right, so set up the context of our problem here. It says here, one night at the Tunisian night casino, renowned gambler Jeremy Turner, aka the Missouri Master, is having a fantastic night at the craps table. In 2 hours of playing, he has racked up over $30,000 in winning and showing no sign of stopping. Crowds are gathering around him watching his streak, and the Missouri Master is telling everyone with earshot his good luck is due to the fact that he's using the casino's lucky pair of bruiser dice, so named because one is black and the other is blue. Unbeknownst to Turner, however, the casino statistician has been quietly watching his rolls, marking down the values of each roll, noting the values of the black and blue dice separately. After 60 rolls, the statistician has become convinced the blue die is loaded. So here are the results. You can actually start to see in the results there's a lot more 1s and 6s and not so many 2, 3s, 4s, and 5s. So at first glance, the table would appear to be strong evidence that the blue die was indeed loaded. There are more 1s and 6s than expected, fewer of the other numbers. However, it's possible that such differences do occur by chance, so it's possible we could have gotten this result. The question is, what is the probability of this? And that's what we're going to do. Is this result due to chance variation, or do we have statistical evidence that the blue die is loaded? Perform a test and support your conclusion. So like I said, pause it, try it. I'm going to give you about 3 seconds here, and I'm going to do each part. All right, so my state. Well, the null hypothesis would say the blue die is fair. I'm getting an equal distribution. Okay? The distribution of outcomes of the blue die is the same of that of a fair die. It would be, if you're doing probabilities, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6 for all of them. Okay? The alternative is to say the distribution is not the same. So in our case, we're suspecting that there's more 1s and 6s. but we don't necessarily only know that just because of what we observe. But basically, we're saying it's not the same. So we're going to see, is getting more 1s and 6s here statistically significant? All right, go ahead and pause again. We'll do the plan in just a second. All right, so we state, or sorry, in our plan, we're going to say which type of test. This is the chi-square goodness of fit test. So then we talk about it being random. Statistician collected a random sample of 60 rolls. Are all our expected counts greater than 5? Yes, because they all should be greater than 10. 1/6 of 60, since they're all equal, we should have 10 of each outcome. Okay. Are they independent? Well, one outcome doesn't impact the other rolls, and really you don't technically need the population greater than 10 times the sample. If you said that, that's okay, but I know this is something I haven't talked much about, but if you're doing an experiment and there's an infinite amount of possibilities, like you can roll this die forever, population being greater than 10 times the sample is technically not needed, okay? Even though I know that I've been having you do that on prior tests dealing with like 1 and 2 sample T and P tests. All right, so now go ahead and pause again and we'll do the do part. All right, if you've come back here, let's check out the do part. So chi-squared statistic observed minus expected squared divided by expected. So I'm taking each outcome, my observed from my table, I expected 10, and I'm doing quantity squared dividing by 10. So I do that for the 1s, the 2s, the 3s, the 4s, the 5s, the 6s. Should get a chi-squared statistic of 13.6. My degrees of freedom here, if I think about it, is I had 6 different groups, minus 1, so there's 5 degrees of freedom. So when I calculate out my p-value, chi-squared CDF 13.69995, I get a probability of 0.018. So even though that was a pretty big chi-squared value, you're thinking to yourself, oh my goodness, this is going to be another, close to 0. You'll be actually surprised how big chi-squared can actually be and still produce, even though this p-value is pretty darn small, it's only 1.8%, okay? And it's going to cause us to reject. Oops, I'm kind of giving away the next part. But go ahead and pause, and we'll finish up. All right, so the conclusion part here. So what would we say about our sampling distribution? All right, let me move that up a little bit so it's a little bit easier to see. It's more in the middle of the screen. So we would say that our result from 60 rolls, or one more extreme, would only occur 1.8% of the time if our null hypothesis was true, meaning the die was a fair die. It's less than 5%, so we're going to reject, meaning we do have statistical evidence that the blue die is not a fair die. It's more than likely the casino is going to pull those dice off and give this gambler, Jeremy Turner, a chance, or they'll probably still have him play, but they'll give him either new dice, or if they don't want him to play, they'll just kindly ask him to leave. All right, so that takes care of 11.1 notes. All right, excellent.